Let's take a look at how we find the derivatives of these inverse trig functions and also how they work with our other differentiation rules that we now know. So let's start off with, we're going to work 4 examples here. Let's take the derivative of the inverse sine of 2x. We already did the inverse sine of x, but now let's take a look at 2x because we need to understand when we look at those formulas we have on the previous video, we need to kind of really establish our u as the argument inside of these inverse functions. So my u, when you see me apply this to the formula that we came up with, the u is going to be equal to 2x. So this equals, well, it's going to start off with the derivative with respect to x of u in the numerator. That's 2x, so that would be my u prime, all over, it ends up being the square root of 1 minus u squared. Well, remember u was 2x, so 2x quantity needs to be squared, and I end up with this right here. So here's my u prime. Again, understand that u is the argument inside of inverse sine. Here's my u prime. Here's my square root of 1 minus u squared. And then if I just do a little bit of simplification here, this ends up being 2 in the numerator. If I square 2x quantity squared, that's 4x squared. So this is 2 over the square root of 1 minus 4x squared. And that's about as simplified as we can get it. Let's also take a look at the derivative of the inverse tangent of 3x. We'll see how inverse tangent works. That's the first time we've worked with that derivative so far. Well, it is u prime over 1 plus u squared. So again, my u is 3x. So I want to start off with the derivative with respect to x of 3x. There's my u prime, all over 1 plus my u, 3x quantity squared. Well, the derivative of 3x is 3, all over 3x quantity squared is 9x squared, 3 over 1 plus 9x squared. And so there's the derivative of that. Again, if you can identify what your u is, it's pretty easy to substitute them into those formulas we have for the derivatives of those inverse trig functions. All right, let's take a look at how the chain rule comes into play here. So the derivative with respect to x of the inverse secant of e to the 2x. And so I've got inverse secant acting on a function of x, and this actually within itself is a composition of functions. So when we look at the derivative of inverse secant, we want to start off, it's got u prime in the numerator, so that's the derivative with respect to x of e to the 2x over the absolute value of u, which is e to the 2x, times the square root of e to the 2x quantity squared minus 1. And so that's where I'm at right now. Again, if you understand that e to the 2x is u, here's u prime, here's the absolute value of u, square root of u squared minus 1. All right, so let's talk about what we have here. The derivative of e to the 2x, well, I'm going to have to apply the chain rule again here because this is e to the something. The derivative of e to the something is e to that something times the derivative of that something. So the derivative of e to the 2x, e to the 2x times the derivative of 2x. All over, again, I'm going to have the absolute value of e to the 2x. Here, if I've got e to the 2x quantity squared, remember a power raised to a power, I can multiply those exponents. So this is the square root of e to the 4x minus 1. Now, a couple of things that happen here before we get our final answer. E to the 2x over the absolute value of e to the 2x. You might be looking at that and thinking, does that cancel? In this particular case, yes, we can. E to the 2x, think about an exponential function. That's always positive, so the absolute value is really not in play here. E to the 2x over the absolute value of e to the 2x, those are going to cancel out. They're always positive, so I don't have to worry as much about the absolute value. So those are going to cancel, and I'm left with the derivative of 2x in the numerator, which is 2 over the square root of e to the 4x minus 1, and there's my derivative. Last function that we'll take a look at, let's take a look at the derivative with respect to x of x squared times the inverse tangent of 5x. This is a product of functions. It's the product of x squared times the inverse tangent of 5x. So I'm going to use the product rule that says the first function times the derivative of the second function plus the second function times the derivative of the first function, like so. Okay, so derivative of inverse tangent of 5x, my u is going to be 5x. So this is x squared times u prime. So the derivative with respect to x of 5x is in the numerator over 1 plus u squared, well, 1 plus 5x quantity squared. So there's my derivative of inverse tangent of 5x. Over here on this other piece, I have the derivative of x squared. That's 2x. So this is 2x inverse tangent of 5x. And then just to kind of clean up my answer here, the derivative of 5x is 5. I'm going to go ahead and multiply that x squared into the numerator. So that is 5x squared over, if I take 5x and I square it, this ends up being 1 plus 25x squared plus 2x times the inverse tangent of 5x. And we'll go ahead and call that good right there because we'll look at some simplification things later on. But there's the derivative of that particular product of functions. So really when it comes to these inverse trig functions, figure out what your u is. What is the argument inside the inverse trig function? Because you're going to have to make sure, as we saw in multiple examples, that we apply the chain rule there. It's also important because if you come back up here to one of these simpler ones, if I know that u is 3x, that needs to be squared, for example, on this one in the denominator. So if I can understand what my u is, it becomes very easy to kind of work with these formulas for the derivatives of the inverse trig functions, which can also be combined with the chain rule, the product rule. We could have done an example with the quotient rule. All of those things could have been in play. So yeah, there's a lot to kind of know, and that's why you practice, to make sure that you understand how all of these things work together.